Hello, fans of GeoGebra. We have a very basic example here starting at the lowest level. We have a horizontal beam that is pinned at the left end and a roller support at the right. What the pin means is that it is restrained from vertical movement up or down, and it is restrained from horizontal movement left and right. What the roller support means is that it's restrained from movement up and down, but it is free to roll, and that's why we call it a roller, on the surface that it's resting. So we don't see it here, but there's a horizontal surface. The beam is subjected to some gravity loads, gravity being downwards, and the distribution is known, and the start and the stop of the load is known. And the question is, what equilibrating force would be under this reaction holding the beam in equilibrium? How we do that is we perturb the beam, and what that means is that if we're looking for the vertical reaction, we need to perturb the vertical movement of the support without changing anything else. So the beam itself does not distort, it simply rotates about the left point. So you draw a circle centered around the left point with this radius beam length. But here's the little puzzling part. The load looks like it is traveling with the beam, and it looks like it should be perpendicular to the beam. But what we're pretending here is very, very small displacements, and that's why we use the word perturbed. It's just a little breath. It's not a big push like this, but I distort it wildly so you see it in its grossly deformed shape. One of the puzzles that students have with this method is the following. What we need to do is find the centroid of where the distributed load is. This shape is known, so the centroid is easy to find, especially with something like GeoGebra, a computational drawing environment. And we put that net force at the centroid of that distribution. In the distorted position, we have to track where that distorted load, the load is in the distorted case. It's still at the centroid of the shape, but it's downward. It is not perpendicular to the beam. That's the hardest part. So just track the net load, and as we perturb it, and it's very, very small, you'll see it. So the perturbation is how much does the horizontal ground move vertically? What is that violation of a boundary condition? But how much it moves left and right is not a violation of a boundary condition, so we don't have to track that at all. So what we're doing is watching how much the support moves vertically. We're ignoring how much the support moves horizontally because there is no restraint there. And then we are watching how much the vertical load moves vertically. That's the net vertical loft, what I'm calling. How much it moves horizontally is inconsequential because it is a vertical load, so there's no work done by its horizontal movement. The work is only in the direction of the force. We have negative work here because the load is going down and the loft is going up, so they are opposing each other. So the work of this load plus the work of the reaction load must be zero. This left support does no work because it's not moving. So I shifted the arrows to be vertical here, and I'm only going to track the vertical loft. And then I will move this down, 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 really, really small, and that will be the answer. The reaction times the perturbation minus the gravity times the loft is equal to zero. So I bring the gravity and the loft over to this side, and I find the reaction. And that's exactly what we do here. We just move this down, 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 down until this is teeny tiny, teeny tiny. And boom, that is our answer. That is our answer. Okay? Okay.